section 14.1, limits of functions. Our objective is to use the informal definition of a limit. Now, in this section, we are going to focus on graphically finding the limit and using our graphing calculator to help us do that. And in section 14.2, we're going to focus on algebraically finding the limit. So I'm going to do a little bit of both in this video. Now, many mathematical problems involve the behavior of a function at a particular value. For example, the question is, what is the value of a function f of x when x is equal to c? Now, we've done this before, like for example, let's say that f of x is equal to the function x squared, and we wanted to evaluate the function for an x value of 2, well then we would plug 2 into the equation for x and solve, and when we solve we get 2 squared, which is equal to 4. Now, the underlying idea of a limit is the behavior of the function near x equals c and not at x equals c. And the reason that is because we're going to be discussing limits that can be reached and that limits that cannot be reached. So limits that can be reached means that the value of x that you're approaching is in the domain of the function, whereas limits that cannot be reached means that the value near x equals c is not in the domain. So that's when we have to do other things in order to figure out what that value would be reaching. And when I'm talking about this value, the limit is the height of the value as you're approaching x. So first let's talk about limits that can be reached. And again, I'm just going to write down that means that it's values of x that are in the domain. So the value of x is in the domain of the function. So I call these easy limits, and I'll show you why in just a second. So we want to find the behavior of the graph f of x equals 3x minus 2 when x is very close to 2. So the way that we write a limit is by the following. So the limit, and notice that underneath it's written smaller, so that says x and that arrow means approaches. So the limit as x approaches 2 for the function 3x minus 2 is what we're trying to figure out. So I'm going to write that in words. The limit as x approaches 2 for the function 3x minus 2. So that's what we were doing. Now, for this problem, because if I plug 2 into my equation just to show you, so I know I get 3 times 2 minus 2. Because 2 is in the domain of the function, and the domain of this would be all real numbers because there's no variables underneath radicals and there's no variables in my denominator. So because of that, we can just plug 2 into our equation and actually figure out, well, 3 times 2 is 6 and 6 minus 2 is 4. So I know that the limit as x approaches 2 for this function 3x minus 2 is equal to a value of 4. So that's why these are easy limits, because when it's in the domain, you can just plug the number in. So we can also graphically show this. How do we graphically show this? We have to look at values of x as we come very close to 2 from the left side of the graph and from the right side of the graph. So here's an x value of 2. And if you look right here, this is the point that we are looking at. So we're trying to see what is happening to the height of our graph at values of x as we come from the left and the right. So from the left side, as we're going this way towards our graph, so this would be as x approaches 2, and we write a little negative sign to stand for the left. Well, when a limit doesn't exist, this is why we have to do this part. So values that approach 2 from the left are values that are less than 2, such as 1.9, 1.99, 1.999, and of course I could keep on going, but I'm not going to put in 2 because we're trying to find this value right here of 2. Then values that approach from the right is on this side of the graph. So this would be as x approaches 2 when we use a plus sign to stand for the right. So as x approaches 2 from the right, what are our y values coming closer and closer to? Now notice that my value of 2 from the right, as we're going this way, we get values such that are very close. 2.1 and then 2.01 is even closer. 2.001 is even closer to that value. Whereas when we're doing the left side, we go this way. So I think of the left side as the negative side, which is why we use a little minus sign, and the right side as the positive side, which is why I use the plus sign. So in order to do this, we can use our graphing calculator. So in your graphing calculator, you would plug in the function into your y equals. And of course, we could go ahead and hit zoom 6 and look at a nice graph. If you go to second window, and let's change our independent variable to ask, and I'm going to hit enter. So when I do that and go to my table, second graph, and I plug in these values, if I plug in 1.9 and something even closer, 1.99, these are values approaching 2 from the left side, I can see that I'm coming closer and closer and closer to the value of 4. So as we approach from the other side, which is the right side, we would need values such as 2.1. Something even closer would be 2.01. Even closer would be 2.001. And of course, we could keep going. So notice that values from the left side are approaching 4, values from the right side are approaching 4, and of course, because the value of 2 is in our domain, we know it's actually equal to 4 at that spot. So we can write these values in. So this one was 3.7, 3.97, 3.997. Here we had 4.003, 4.03, and 4.3. So the closer x gets to 2, the closer that the function gets to the value of 4. And again, for something like this, it's easy because really we didn't have to do all that work. We can just plug 2 into our equation and solve. But what happens when it's not defined at the value is what we're going to be looking at in a little bit. So let's look at the next one. The definition of a limit. If f of x becomes arbitrarily close to a unique number L as x approaches c from either side, the limit of f of x as x approaches c is going to be equal to L. That's just the definition. So let's look at the following limits. Now, we have the function x cubed here. So x cubed, I know my domain is all real numbers. If I want to find the limit as x approaches 3, that means I'm just going to plug 3 in for x because it's within the domain. So when I do this, I don't have to worry about looking at my graphing calculator because all I have to do is just go ahead and plug this in and I get 27. Now let's look at the next one, x plus 4. So it's just a line. I know my domain's all real numbers. So I want to find the limit as x approaches -2 of x plus 4. So for this, again, we can do the same thing. Plug -2 in for x. When I do that, -2 plus 4 is a value of 2. So I know that the limit as x approaches -2 for the function x plus 4 is equal to 2. So again, that's why these are called easy limits, because it's the values that we're approaching are within the domain. So let's find the limit that cannot be reached. So that means the value is not in the domain. For example, if we look at this next problem, we want to find the limit as x approaches 1 for this function. So if I plug 1 into this function right now as it is, we have 1 cubed minus 1 squared plus 1 minus 1 over 1 minus 1. Now, if I try to solve this, notice right here in my denominator, I'm going to get a value of 0. And remember, we can't divide by 0. Because of that, we have what's called, in this case, a hole of our graph. And if you look right over here, you can see the graph, and there's a hole right here at an x value of 1. Now, that's why it's easy to graphically be able to look at what's happening at this value by plugging into your graphing calculator and looking as you approach x equals 1 from the left side of our graph, what's going to be happening, and what happens as we approach, as x approaches 1 from the right side. So that's where we get these values, 1.1, 1.01, 1.001, and over here for the left side, 0.9, 0.99, 0.999. So we're saying, as we go along this graph, where are we going to be going towards for the left side? And as we come to this point, what are happening to our y values as we come from the right side of our graph? Now, to do that, because we have 0 in our denominator, we couldn't plug it in, so that's why we can use our graphing calculator. So you guys should also practice putting this into your calculator. So I put the function into y equals. I changed my window back to auto right here, and then I hit graph zoom 6. Now, if you look at my graph, I can't tell that there's a hole at an x value of 1 because our graphing calculators don't show that. If I do second trace value and plug in 1 for x, you'll notice that the y value doesn't come up because it's not really there. And if you go to your table now that we've changed it back to auto, notice that x equals 1, it says error. So we are concerned with what's happening as we're approaching this value. That's what makes limits so cool, is that we can do that by graphically looking at them or algebraically. So right now we're just focusing on graphing. So if I go to my table set, I'm going to put it back on auto, and then go to my table, and I'm going to plug in values as I approach x from the left and the right that are very close to a value of 1. So values that approach from the left, so less than 1, would be 0.9. Something even closer would be 0.99. Even closer would be 0.999. And I could keep on going. And if you notice as you do this, your values are becoming closer and closer to looks like to a value of 2. So now let's go and do the other side. As I approach from the right side, so values above 1 but very close to 1 would be 1.1. But we can do even better than that. We can get even closer by doing 1.01. And we can get even closer by doing 1.001. And even closer would be 1.0001. And notice that these values are coming closer and closer to 2 from the other side of our graph. So if we plug these in, we had 1.8, 1.9801, 1.998. This is what we were looking for. 2.002, 2.0201, 2.21. And we can tell, because both sides are coming close to a value of 2, that the limit appears to be 2. So I would say that the limit as x approaches 1 for this function, x cubed minus x squared plus x minus 1 over x minus 1 is equal to 2. Now, in the next chapter, just to get a little ahead of myself, we can actually algebraically do some stuff in order to figure out what the limit's going to be. So algebraically, what could I do here? Well, if you remember when we did rational functions, we could do factoring in order to maybe get rid of that x minus 1 in my denominator. So if I do factoring for this, I can factor by grouping in my numerator. So when I do that, I get x squared times x minus 1 plus, and I'm not going to factor anything else from the second one, because that gives me x minus 1. And when I do that, x squared plus 1 gets a set of parentheses times x minus 1, because we factor out the x squared and the 1, over x minus 1. And notice that these cancel out. So when we simplify this, x squared plus 1 would be the simplified version. And what we're going to learn in section 14.2 is that the limit, if you simplify it algebraically, the limit as x approaches 1 for x squared plus 1 would also give me the answer for this. So if I plug 1 into this equation, now that we got it out of our denominator, I would get 1 squared plus 1, which is equal to a value of 2. So that's another way that we're going to do it. But like I said, right now we're really focusing on graphing, but I wanted to show you that's what's going to be coming next. Now let's look at another example. So here's another one where we have the limit as x approaches 0 for this function. So again, for this, if I plug 0 in here, I get the square root of 0 plus 1 and then minus 1. So when I do this, I have 0 over the square root of 1 minus 1. The square root of 1 is just 1, so 1 minus 1 is 0, so 0 over 0. And again, we can't divide by 0, so how do I go about finding what the limit is as x approaches 0? And remember, that means we want to figure it out as x is approaching 0 from the left and as x approaches 0 from the right. Now, again, we graphically look at this in our calculator to do so, and if you were to look at the graph over here, so this is as we're approaching from the right, as we're approaching from the left, I can tell looking at this graph that I'm going to be approaching the value, y value of 2, but let's go ahead and check with our graphing calculator and plugging in for our y equals. So I plugged it into my y equals. If I look at my graph, notice that you can't tell in your graph that there's a hole at x equals 0, but if I hit second trace value 0, I notice that nothing comes up for the y value because it's not really there. There's a hole in your graph. Now, if I do my x values as x approaches from the left side, I know that as we approach x from the left side, which means we want negative values towards 0, we can do negative 0.01, negative 0.001, negative 0.0, negative 0.0001. Oops, I didn't put the wrong one. Negative 0.0001. And then for that one, notice it came up like this. This just means you're moving your decimal place 4 places to the left. Notice it comes up as 2 if you look here. However, it's not really equal to 2. It's just that it's very, very close to, and I forgot to put the negative in there, so negative 0.0001. It's just very, very close to 2. So the more I keep getting closer and closer, your calculator is actually just going to display the value that you're reaching, even though it's not really reaching that value because our graph is undefined at that value. And notice it puts 2 here, but if you scroll over, notice it's just very, very close. So if I do the other side as we approach from the right, so delete these out. Values as we approach from the right are going to be things such as 0.01 and 0.001, etc. And notice that we're also approaching the value of 2. So that's what we did and graphically. So this was 1.995, 1.9995, 1.9999. This we don't know. 2.0001, 2.0005, and 2.005. So again, we were coming closer and closer to the value of 2. So it's easy when you're given a graph like I have right here because you can just look at the graph and tell. You guys won't have these graphs, so you'll have to do it in your graphing calculator and make a table on your own. Let's look at another one. And just to go back to this one, there is a way you can algebraically find this limit, but like I said, we're not focusing on that right now. We'll do it later. So let's find the limit as x approaches 3 for this piecewise defined function that we have. So for this piecewise defined function, if I have the first one, we have noticed just 2. Remember, that really means you have y equals 2 for values of x not equal to 3, and the second one says y equals 0 for only for values of x equal to 3. And this is what your graph would look like. So let's do that in our graphing calculator. So in our graphing calculator, if you go to your y equals, we would have 2 and then hit the comma, and then if you put parentheses, remember we can do x and then go to second math. And then we have these symbols, so number 2 not equal to 3, because this is a piecewise defined function. We showed this earlier in the year. And at 0, we want only for an x value of 3. Now if I hit graph here, oops. I missed, oh, it's supposed to be, I'm sorry, it's not the comma, it's the division symbol. I forgot. So we'll fix that. So put the division symbol to do that. I was thinking of my other program. So if I hit graph, now this is what my graph looks like. Now if I hit second trace value of, we're doing 3 for the limit, notice that for this line right here, it says nothing, and if I scroll to the right, I would be on my other function. Notice I get, I would get a, oops, trace. So if I go down, notice I get 3, 0 is 3 for this other function that we would have. Now, for this, we would write this as the limit as x approaches 3, and instead of writing in the piecewise defined function, just write f of x. So in this case, the limit as x approaches 3 is a little bit harder to find because notice that your y values as you approach 3 from the left are approaching a value of, it looks like 2. And as you're approaching from the right, we're also approaching a y value of 2. So the limit as x approaches 3 for this function would be equal to 2. Even though for this, if I did f of 3 into this equation, well, f of 3, we can't use 3 here because it's not equal. I would have to use this one. F of 3 is really defined at an x value of 0. But the problem with that is you have to remember that a limit is the value as x is approaching values of y near that x value. And if we are on this part of my graph up here, well then that means we're really approaching x values of 2, and it would not be equal to a value of in this case, a y value of 0. Even though we do have this point right here, we cannot use it. So that's usually where students get a little bit messed up, is because they think that the limit as x approaches 3 for this function should be equal to 3. However, it's not. It's equal to the y values that you're approaching as you approach an x value of 3. Now, the limit of a function, f of x, as x approaches c does not exist if any of the following conditions are true. So the first case is f of x approaches a different number from the right side of c rather than from the left side of c. So if we look here, now for this function, this is what we were just talking about. As I approach my graph from the left side, notice I'm approaching y values of 2.5. So we could write that as the limit as x approaches c from the left side, which we would write a little minus there for this function, would be equal to a value of 2.5. And we're going to do one-sided limits later on. And the limit as x approaches c from the positive side or the right side of the function, f of x, notice is approaching this value right here of 4.5. Because these two limits are not the same, then I know that the limit as x approaches c for this function does not exist. And usually we write d n e, so does not exist. Well, let's look at the second scenario. So now for this one, and I should have gone back over here, f of c for this function is not defined. And that means that I can never ever have a c value there. Whereas if you look at the second graph here, the value of c is defined because of this closed circle that we have. So f of c would actually be equal to this value that we had in the last one, which is 4.5. However, even though it's defined, as we approach our value of c from the left side, we're still approaching 2.5. From the right side, we're still approaching 4.5. So the limit as x approaches c for this function still does not exist, even though we have a value of c that is defined. So if you look at the third graph here, now we have a different value of c that's not part of their function. So f of c in this case is equal to, looks like 1, 2, 3, 4, 5, 6.5 maybe. But the limit as we approach C from the left side is still 2.5, from the right side is still 4.5 because they're approaching two different values. The limit as x approaches C for this function still does not exist. It has to be approaching the same number on your graph from the left and the right for our limit to be able to exist. Now, let's do some more examples. So here's an example of that. We have the limit as x approaches 0 for the absolute value of x over x. So you could graph this in your calculator. And to graph it, you can do second catalog. The first one's absolute value of x divided by, divided by x. If I hit graph, this is what my graph looks like. If I change my values here, let's start this with auto and not ask, and go to my table. Notice that at 0, we have an error, and at -1, we have -1. And here, if you look at our graph, notice that we can't plug x values of 0 in here, because if we do, we would end up with the absolute value of 0 over 0, which is just equal to undefined. So, because we can't divide by 0, but I need to figure out what the limit of this is equal to. So to find the limit, if I look, the limit as x approaches 1, or not 1, sorry, the limit as x approaches 0 from the right side, so this is as x approaches 0 from the right, and this would be the limit as x approaches 0 from the left. So this one is approaching a value of 1. This one is approaching a value of -1. Therefore, the limit does not exist. And the reason you can kind of tell is because, remember, if I plug 1 into this equation, the absolute value of 1 over 1 would just be equal to 1. If I plug in -1, the absolute value of -1 over 1 would be equal to positive 1. Sorry, over -1, so it would be equal to 1 over -1, which is equal to -1. So any of our negative values will always have this negative in the denominator. So as we approach 0, we're going to get closer and closer to -1 for the left side and to 1. And again, because it's approaching two different values, that is why the limit does not exist. The next case is when our f of x increases or decreases without bound as x approaches c. That just means decreasing or increasing without bound is just means that your graph is going to infinity or negative infinity. So if we look at this graph right here, the limit as x approaches 0 for 1 over x squared, notice that as I approach from the right side and from the left side, and I guess I should do it on the graph because we are always on our graph. So as I approach from this way and from this way, from the left, notice that our y values are going up to positive infinity. Because they're increasing without bound, that means that the limit does not exist, so we'll just write d and e. And why would that be? Remember that infinity is not a number, because it's going to be increasing and keep on increasing forever and ever, and so because of that, we would not really have a limit. Now, later on, sometimes we do actually write that the limit as x approaches 0 for 1 over x squared is equal to infinity, but we'll talk about that later. So for right now, when it approaches infinity, it would not exist. Or even if I have a graph that went like this, where one side goes up and one side goes down. So for this graph right here, the limit as x approaches 0 for this function would also not exist. And even if I had both my graph parts for my arrows going downwards towards negative infinity, it would also not exist. The last one is when f of x oscillates between two fixed values as x approaches c. So the limit as x approaches 0 for the sine of 1 over x is a graph that looks like this. Because these values are going back and forth between 1 and -1, the limit does not exist. So if you graph it, sine of 1 over x, make sure you're in meridian mode, hit zoom 7 for a nice trig graph. If we look here, it's hard to tell what's going on there, so then I would just zoom in. And if you notice, the more and more you keep zooming in, if I hit enter again, I'm going to zoom in again, these values are just going back and forth and back and forth. So because of that, I know that if I hit trace, at 0 we had nothing, but if you look from the other side of 0, it's approaching a negative value, and then the positive side, it's approaching a positive value. And if you put it into your table, you would also notice that you're approaching a negative and positive value, so therefore the limit doesn't exist. So be careful. So just to recap, we have limits that exist and limits that don't exist. And we have limits that can be reached and limits that cannot be reached. Limits that can be reached are values of x as you're approaching them that are in the domain. Limits that cannot be reached are values of x that are not in the domain. And limits that can be reached mean that the limit exists. So you're coming towards the same value from the left and the right side as you're approaching that x value, and limits that go to different values as you approach from the left or right, or that increase or decrease without bound, or oscillate back and forth between fixed values do not exist. So make sure you bring this with you to class, and we're going to do some more practice.